In the previous approach, we have chosen to generate all the solutions, and then we will filter them at the end when we have taken a decision for all the decision variables. And we wait until all the decisions are taken just to filter them. We might optimize a little bit this approach. Actually, it will be really a big speed up if we, instead of waiting until the end to check if the solution is a solution or not, we will also check partial solutions. It means that we could backtrack much earlier in the search tree. So, for instance, we might detect that as soon as we assign the queen number 4 here, we detect a failure here. We detect that it's not feasible because it's already violating some constraints between queen number 4 and the previous queens that we have decided before. Okay, so that's really an improvement over the previous approach. And the implementation is not really more difficult to do. Instead of checking the solutions here when we detect that we are at the end, so when we detect that the current index is equal to n, which means that we have decided all the variables, we could, instead of that, verify that the constraints are satisfied on partial solutions. It means that as soon as we have decided the next queen, we immediately detect if it's feasible or not with respect to the previous decisions. And so constraint satisfied now is not a void method, but it has one additional parameter, idx, which is the next index that has just been decided. So j here is just the index that we have decided. And instead of detecting for every pair of variables, we just need to detect for the previous variables. So we just need to check the decision at index j with respect to all the previous decisions, so from 0 until j-1. And so if we detect that some of the queens on this prefix are already on the same row or on the same diagonal, then we can return false, which means that we will not call the recursive method here of the DFS, and we will backtrack. All this works very well because we are reusing the memory. So Q, the array Q, will be reused on backtrack. So it means that when you will backtrack to a previous state, so let's say that you will backtrack and try an alternative here, it means that you will erase, okay, the subsequent variables. So if you backtrack at a position 2, for instance, you might erase the decision that you have taken before, and that's fine because you always verify with respect to the prefix of the decisions and not the suffix of the decisions. Okay, so all the ones, even if you have already considered them in the past, a little bit at a lower position before in the search tree, it doesn't matter because you are only verifying here with respect to the prefix or values at index I that are less than j, and j is just the last decision that you have taken. So that's really a search per level. The backtracking can only work up to index I, and then as soon as you didn't decide it yet, the level I, you cannot move to the next level I+1. That might be a limitation of that approach, okay? So in some situations, it's more efficient for problems to really decide in a dynamic way what is the next decision that you want to take. Here it's not possible. It's really fixed in advance. You will always progress in the array Q in a growing index fashion. Also, a limitation of that approach is still that the problem is a little bit hard-coded, right? If you take the class here, NQueens prune, you see that the constraint satisfaction verification is really hard-coded in the middle of the depth-first search. So if you want to change a little bit the problem, and let's say that instead of the NQueens, you would like to solve a Sudoku problem, then you need to re-implement it and do a copy-paste of this approach and adapt it. So that's not yet fully generic. In the next version of our implementation, we will really aim at doing something that is very generic, in which you can reuse all the ingredients as if it was a library. And we will call that a constraint satisfaction problem solver.